So in today's lecture, we'll be dealing with the per unit problem. Okay, it is a special case that we'll be considering for today's lecture. Okay, so I have already told that about this problem, right? So yesterday's at the end of the yesterday's class, I have given the question for this problem, and in this problem, there's a single generator. Okay, there's a single generator followed by at the rightmost end we are having a load motor. Okay, so in between we are having four transformers. In between we are having four transformers. So what we'll be seeing is that we'll be deriving the reactance diagram for this question. Okay, we'll be drawing the reactance diagram for this, and after that again this problem will be further extended as a special case. Okay, so in such criteria how we can solve this problem I'll be telling you. So coming to the problem, as I said, they have asked to draw the reactance diagram. They have asked us to draw the reactance diagram. They have asked us to draw the reactance diagram by keeping the common base value as your generator. So your generator remains as a common base value, and from this what we can say is that can get into the solution. Okay, so here we can just write given. So from the given criteria, the common base MVA from your generator is equal to 100 MVA. Okay, followed by your common base KV. So these two represents your new value is equal to 22 K. Okay, so the main formula what we will be using is, so the formula what we will be using is the same common formula for per unit. Z per unit nu will be equal to Z per unit given, okay, into your base MVA nu divided by base MVA given into base KV given divided by base KV nu the whole square. Okay, this is the formula, and with respect to this formula, we can first write for the generator. So for this generator, where Z per unit nu for generator is equal to, so as per the question, the reactance what they have given around 0.18. Okay, so they have given around 0.18. They have to consider that. So 0.18. So you are considering your taking the common base value as your generator. So both the base MVA new and base MVA given will be the same. So it will be 100 by 100 into base KV given and new will be the same. It will be 22 divided by 22 the whole square. So you'll be getting the answer as, this gets cancel. So you'll be getting as J 0.18 per unit. Okay, so this is what the per unit impedance for your generator. So moving on, now we will be getting with respect to the transformer 1. Okay, P1 T1. So we'll be considering the primary. Okay. The thing is that it is not necessary to consider both primary and secondary in all the problems. Okay, that you have to be clear. So for a simplification process, you can just consider the primary on all the four transformers. But the thing is that you have to calculate the revised voltage, because from the primary to secondary you will be having a jump. Okay, you'll be having a jump. So at the time you have to find the per unit for this transmission line also. So this transmission line per unit calculation will be based upon the revised voltage at the secondary. Okay, so with reference to the primary, you can just find your per unit for the transformer, and after that you have to find your revised voltage at the secondary. I will be telling, you just follow on. So now we'll be considering only the primary, so it will be T1 with reference to 22 kV, which is nothing but your primary. So Z per unit U for your T1 is equal to, so it is rated at 0.1. So base MVA is your generator MVA, so 100, and the given MVA is 50 into the base voltages remain the same. So it will be 22 divided by 22 the whole square. Okay, so this gets cancelled out, so this gets cancelled, so this gets cancelled, so we'll be getting 0.2. We'll be getting the value as J into 0.2 per unit. Okay, so this is what with respect to the primary. So after finding the primary, you have to consider your revised. Okay, for the revised, since you are going to make a jump from your primary to the secondary. Okay, so for revised kV, as you know, it is nothing but the given kV into your transformer ratio. So how we can find this? So revised kV new for your T1 will be equal to, it is the given kV is 22. Okay, 22 into your transformer ratio, it is 220 divided by 22. So you'll be getting around 220 kV. So this is your revised voltage, and this revised voltage is the voltage drop which is across the secondary of your T1. Okay, secondary of your T1 to your primary of your T2. So the transmission line impedance, the revised voltage will be 220 kV. Okay, so this is what with respect to your T1. At the same time, now we will be considering the T3. Okay, so T3 is the another one transformer which is connected to the same bus, same source bus. Okay, so this bus. Okay, so now we'll be considering a T3. So for T3 with reference to 22 kV. Again, here you can only consider your primary. And what happened over here is Z per unit new for your T3 will be equal to 0.065 into, okay, base MVA is 100, so the given MVA is 40, the base kV is 22, by 22. Okay, the whole square. So this gets cancelled, this gets cancelled, and you'll be getting 10 by 4, and the value what will be so I had some problem with the network issue. Okay, and over here, so you'll be getting the Z per unit nu as for your T3 it will be 0. It will be around it will be around J into 0.1625 per unit. Okay, and over here your next you have to find your revised kV, revised kV new for your T3 is given by 22 into, so here the transformer ratio is 110 by 22, so that you have to consider. It will be 110 divided by 22, so the voltage will be 110 kV for the other branch. So for this branch the voltage will be 110 kV. Okay, so after this we will be moving towards the T2 referred to 220 kV. Okay, and for this Z per unit nu of T2 will be equal to 0.06 100 by 40 into 220 by 220. So this is nothing but your revised kV new for your T1. Okay, so that's the value over here, the whole square. So this gets cancelled, so this gets cancelled, this gets cancelled, and you'll be getting the Z per unit new will be equal to 0.15 per unit. Okay, and now with respect to T2, here you can see we are again making a jump from the primary to secondary. So if you are making a jump, as I said, you have to revise your kV. So now what happens? So now what happens? Your revised kV new of T2 is equal to the given kV, which is 220 into the transformer ratio. So it is 11. So it is 11. So here you can see the secondary is 11. So 11 by 220. So you will be getting 11 kV. Okay. So this is what with respect to a T2 refer to a 220 kV. Now we will be moving to T4. T4 referred to 110 kV. Okay. And for this, Z per unit mu T4 will be equal to 0.08 into 100. So it is a base MVA of your generator 50 into 110 by 110. Okay, so this gets cancelled. This becomes 2. So finally we'll be getting J 0.16 per unit. And after this, again you're making a jump from your T4 primary to your T4 secondary. So what you will be doing, you have to revise your kV. So a revised kV new of T4 will be equal to 110 into 11 by 110. So you'll be getting us 11 kV. So this is what with respect to your uh, transformers. Okay, so we have finished all the 4 transformers, and now we will be moving towards your load side. Okay, before load side we will be seeing your transmission line. So afterwards we will be getting towards your load side. So for the transmission line, as you know, the formula what you'll be using is Z per unit is equal to actual impedance by your base impedance, since they have given you a reactance value. So actual impedance divided by your base impedance. So your base impedance will be equal to which is equal to base kV so base kV. So over here uh, actually I'll be putting base kV square by base MVA. So this is the common formula. And for the branch 1, you can consider for branch 1. So for the branch 1, so it will be base impedance will be equal to base kV, and it will be new. Okay, that is the revised base kV you have to consider. So revised base kV new of T1. So you are considering this. As I said, across the transmission line, your voltage is the revised voltage of your transformer 1. Okay, so you have to consider that voltage, and this will be divided by the base MVA, which is nothing but your 100. So we'll be getting around 220 square by 100. Okay, now substitute this in your Z per unit. Okay, so Z per unit nu of branch 1. So branch 1 will be equal to, so over there the actual impedance what they have given is 50 divided by the base impedance what you have calculated 220 square divided by 100 divided by 100. Okay, so on solving you'll be getting J 0.1033 per unit. Okay, I hope you understood with respect to the branch 1. So now we'll be moving towards your branch 2. So in your branch 2, the base impedance is equal to revised base kV nu of T3 divided by your base MVA. So we'll be getting around 65, sorry, not 65, we're getting around 110 square divided by 100, and here your Z per unit nu for branch 2 will be equal to 65 divided by this value by 100. So we'll be getting J 0.5371 per unit. Okay, so this is what with respect to your second branch. And finally we'll be moving towards your load, which is nothing but your motor. So for your motor will be Z per unit nu for the motor will be equal to 0.2. Okay, base MVA is 100, the given MVA is 70, and the voltage will be, so for here the voltage what you have to consider is, you have to consider the voltage what we have revised. Okay, so don't take the voltage what we have taken as the base. Okay, here you should not consider your generator base voltage. Okay, you have to come across your single line diagram. Okay, so at this point of view, what is the voltage you have to consider is the 11 kV, because that is the revised voltage after the jump what we have got. Okay, the same voltage is the what we will be getting across your T4 after making a jump. Okay, the secondary, at the secondary the revised voltage what we'll be getting is the same. The thing is that you can also cross check in such a way that the voltage at the secondary of the T2 and the voltage at the secondary of the T4 will be the same. So can anybody say why it is same?
Sir, because they are acting in parallel, sir. So parallel
Yeah,
operation of transformers feeding the motor, sir.
yeah, of course it's right. So because both of them are in parallel and they are attached to the same bus. Okay, and so the revised kVA only we have to consider, and as per that the revised kV over here is, and don't get confused. Okay, so it is 11 and it is 11. So that's what we have found with respect to the T4. Okay, this value. Okay, and 11 the whole square, and the value what we'll be getting is around J 0.286 per unit. Okay, so this is what with respect to your motor. I hope you understood. Next we'll be moving towards your reactance diagram.
Sir, how come we took it as 11, sir? The base.
Yeah, this thing, right? So I'll be again explaining. So actually, the question what they have given is that they have given us you have to consider the common base MVA as your generator value, right? So if so, you will be always finding your per unit impedance from your source to your load. Okay. So as he asked, the answer is that we have made a jump from your T2 second primary to the secondary. So at that point of time, here your revised voltage is 11 kV. That's what we have found out, right? So the revised kV new T2 is 220 into your transformer ratio. So it's just 11 kV. So this 11 kV is the voltage that is fed into the bus, load bus. Okay, and hence the same 11 kV will be at your secondary of the transformer T4. Okay, and as per the question, they have given base MVA and base kV you have to consider for generator. So that is for the initial stage. Okay, while moving from your left side to the right side, the revised kV changes, but your revised MVA remains the same. You have to see through that. Your revised MVA is 100 MVA throughout this entire power circuit, but your voltage gets deferred. Why in the sense means at each point of the power circuit, the voltage is stepped up or stepped down. Okay, at each point it is stepped up or stepped down, but the power rating remains the same. And as per that variation, your current will gets deferred, and the equilibrium will be maintained in this network. Okay, so our ultimate aim is to keep the power constant, but you can either step up your voltage. In that sense, your current will be decreasing. Okay, otherwise, if you are stepping down your voltage, your current will be increasing, but throughout the circuit, your power remains the same. Okay, so this is the principle behind this power system network and even this entire subject, power system analysis. Okay, so I hope you got some idea about what you have raised as a question.
Sure, yes, sir. But there are two 11 kVs are given to the motor, no,
Yeah,
sir.
yeah. Here also 11 kV. Here also 11 kV. It's not a problem. Okay, because it is attached to the same bus. As you said, they are in parallel. So if they are in parallel, it is mandatory that you must arrive at same voltages. Okay, it is then only your answer is 10% right. Okay. Uh, so at final step, you have arrived at your 11 kV only. Okay. So I hope. Shall I move towards the reactance diagram? I'll draw the reactance diagram. So the reactance diagram for this will be like this. First, initially starting with your generator. So this is with respect to T1, and this is with respect to T3, and followed by your transmission line 1 branch, and this will be with respect to T2. This will be transmission line 2, and finally your motor. And this will be your T4. and over here it will be 0.18 J. Here it will be 0.1625 J. Here it will be 0.5371 J. Here it will be 0.16 J. And it will be 0.2 J. It will be 0.1033 J followed by 0.15 J. And for the motor it is 0.286 J. Okay, so this is the reactance diagram. I hope you got it. So here, as you can see, both the transformers and the transformer lines are at in parallel. Okay, the voltage drop at the primary of the T1 will be the same as that of the voltage drop to a T3. And next we will be moving towards a special case. Okay, special case. I did just explaining about the special case. If time persists, you just do it. Okay. So the special case is that this is an extension of this problem. The special case is that you'll be adding a load. You'll be adding a load to this point, and if you are adding a load, what is your per unit value you have to consider? So they'll be giving the rating of the load as 60 MVA. Okay, 60 MVA, 10.5 kV, and the power factor also they'll be giving 0.6 power factor. So this is a static load. Okay, why I'm saying it is a static load means they have given the power factor. In the case of a dynamic load, the power factor value will be varying. So the thing is that you have to consider the load for your per unit analysis after finding your motor. Okay, so the special case is that just if you want to just take it as a note. Okay, for that you have to find your real power, reactive power. Okay, so over here for the special case, your real power P is what? S given into cos pi. So this you already know. This you can get from your power right angle triangle. So the unit is megawatt. And for the reactive power, it is Q equal to S given into sine phi. So the unit is MVAR. And for the both the cases, you have to consider the given value of the base. Given base, that is your load. That is your load. Okay. And in this also there arises two conditions. Okay, that is if your okay, the thing is with respect to this real power and reactive power, you have to find your Z per unit, and this Z per unit is generally got by RS per unit. Okay, so this will be whole squared plus XS This formula you might have studied in your circuit theory. You'll be getting the root. Okay. So this is the formula. So for this formula, you have to know what is RS per unit and what is XS per unit. So for this, the value will be RS per unit will be equal to voltage. Okay, the voltage per unit. So your voltage per unit, you can, how you can find, I'll be saying voltage per unit the whole square into your S new, it's not S new, S given, into P by P square plus Q square. So if you want to know the detailed formula about this, you can just refer the ebook that I have posted, and that it will be there. So this is a special case. Okay, in general, they won't be asking any kind of problem with respect to this, but you have to know how. If they're asking, you have to know how you can solve it. Okay, so excess per unit will be equal to the same thing, the same formula, except a few more alteration. So here, instead of your real power, you have to consider your reactive power. So it will be Q by P square plus Q square. Okay. So with this, you can easily find the Z per unit for your load. Okay. So we can see. So here, they have given the load to be 60 MVA, 10.5 kV, which is of 0.6 power factor. And now how we can find it means, for the load, as per the given formula, your P equal to S given into cos phi. Okay, so they have given the value of cos phi. So if you want to know the phi, so as per it, the cos phi is 0.6. If you want to know the phi, you can just take the inverse of it to get the value of phi. Okay, we'll be getting the angle, and over here this is given into cos phi is around 60 into your cos phi value. We'll be getting around 36 megawatt. Okay, so now we'll be moving to the reactive power. So Q will be equal to, again, this S given, but the thing is it is sine phi. So it will be around 60 into sine 0.6. So we'll be getting around 48 MVAR. Okay, so we have found this. So the next step is you have to find your RS per unit and XS per unit. For that, you need the value of your voltage per unit. So voltage per unit is nothing but your actual value by your base value. So your actual kV divided by your base kV. So actual kV, what they have given, actual kV given divided by your base kV new. So that is, over here we will be considering your revised base kV, revised base kV we will be considering, okay, of T4 or T2, anything. Okay, so we'll be getting the value as 10.5 by 11. So it will be around 0.9545. Okay, so we have got the V per unit, voltage per unit. Now we have to find the RS per unit. It will be around voltage per unit the whole square into S. It is S given. Yeah, it is S given into P by P square plus Q square. So I will directly substituting 0.9545 whole square into 60 into the value what you have got as the real and reactive power. So it is 36 divided by 36 square plus 48 square. So we'll be getting the value as 0.9115 per unit as RS per unit. And next we'll be finding XS per unit. So the variation in the reactive power occurs. So V per unit the whole square into S given into Q by P square plus Q square, and this will be 0.9545 the whole square into 60 into 48 divided by 36 square plus 48 square. And over here you will be getting the value as J 1.2147 per unit. And finally, the Z per unit nu for the load is root of RS per unit the whole square plus XS per unit the whole square. So the value what we'll be getting around is J 0. Sorry, this is the given value. Sorry, this is given value. Zero point 547, and after this for the load Z per unit nu is, we have to put the normal formula is it for that we will be using for the finding it. So it will be equal to 0.547 into 100, which is nothing but your base MVA divided by your base MVA of the load is 60 into 10.5 divided by 11 the whole square. So you'll be getting J equal to 0.831 per unit. Okay, so this is a special case, and if they are asking to draw the reactance diagram of it, you have to consider this thing. The only variation is that static load you have to draw like this, and you have to ground it. Okay, so this is what with respect to the load. Okay.
Sir, when how it will be like, sir? They would be giving only the power factor value, sir.
You are saying how we can just identify this special case, right?
Yes, sir.
Yeah, it is very simple, man. That is the first thing is, as you said, they'll be giving the power factor. Otherwise, they'll be giving in the single line diagram such kind of arrow mark. If they are representing with such kind of arrow mark, you can consider it to be a load. Okay. Also, they will be giving the other two parameters also, base MVA and the voltage. You have to see at which bus it is connected. That's also plays an important role, whether it is coming in between or whether it is at the end of the power circuit also you have to see. Okay. So as per the shortage of time, you just I'll be just posting this Jamboard immediately as a lecture number 8. Okay, you just see through this problem, After seeing through this problem, if surely will be arising doubts. So when it arises, you just, if possible, I'll be try to arrange a doubt clearing class. Okay, and apart from this, I have posted the notes. Have you gone through the notes? I have posted the notes.
Yes, sir.
Okay, so in the notes, there are numerous problems. Okay, there are numerous problems. You just see through those problems also. So here it is, the PowerPoint presentation for Unit 1, followed by the notes of your Unit 1. So you also see through this notes, and they have clearly given all the materials in the notes. Okay, starting from the theory and all the parts, and most of the problems are covered. Okay, most of the problems are covered, and in some problems, the thing is that the method of solving the problem varies. Okay, method of solving the problem varies. You just do as per the methodology that I have taught you. Okay, but both are the same. In some cases, first they will be finding with respect to the transformer T2 or T3, like that, the variation goes. Okay, so you just use the methodology what I have taught, and it will be helpful for you. Okay.